Morning. I welcome all of you. I am V.Srinivasa Reddy, Associate Professor of Mathematics, Government Degree College, Ramannapet. This is my fifth video lesson on analysis, and overall this is 30th video lesson in this season. So today I will talk on MONOTONE convergence theorem. First, I will prove the MONOTONE convergence theorem. And using this theorem, we do some problems on convergent. So before going to prove MONOTONE convergence theorem, once again, when you say sequence is called increasing, decreasing, and monotonic. Once again, I will define. First, increasing means the sequence Sn is called increasing if Sn plus 1 greater than less than for all n. So it is called a sequence Sn is called increasing if Sn plus 1 greater than or equal to Sn. That means Sn plus 1 minus Sn greater than or equal to 0. Sn plus 1 minus Sn greater than or equal to 0. So whenever it is increasing, it is bounded below automatically. Already last class I told you increasing and decreasing sequence. And decreasing, a sequence Sn is called decreasing if Sn plus 1 less than or equal to Sn for all n. That is Sn plus 1 minus Sn less than or equal to 0. That is Sn plus 1 minus Sn less than or equal to 0. So finally, a sequence Sn is called increasing Sn plus 1 minus Sn greater than or equal to 0 and decreasing if Sn plus 1 minus Sn less than or equal to 0. So, and also monotonic means or monotone, a sequence is called monotonic sequence or monotone. If it is either increasing or decreasing, it is either increasing or decreasing, and the sequence is called the monotonic or monotone sequence. The sequence is called monotonic sequence, it is either increasing or decreasing. And also we know already last class actually infimum and supremum. Once again I will call a real number m is called infimum, that is the greatest lower bound. So the greatest number of all lower bounds of a sequence is called the greatest lower bound, or it is called infimum. Another definition: a real number m is called infimum of sequence if m is the lower bound of sequence, and any number greater than m is not lower bound of the sequence. So when you say a real number m is called infimum of the sequence if m is the lower bound of sequence, and any number greater than m is not a lower bound of the sequence. That means it is the greatest lower bound of the sequence. So what is the meaning of this? Any number greater than m is not a lower bound of sequence, means it is the greatest lower bound of the sequence. So GLB means greatest lower. Similarly, supremum or least upper bound. So the least number of all upper bounds is called least upper bound, or a real number m is called, capital M is called supremum of the sequence if m is a upper bound and any number less than m is not upper bound of the sequence. So if capital M is the upper bound and any number less than m is not upper bound of sequence, that means capital M is the least upper bound of all, is the least upper bound of the sequence, is the least number of the all upper bounds of the sequence. So these are the we need for the prove monotone sequence. So what is the statement? Monotone convergence. All bounded monotone sequences are convergent. So that means every bounded monotonic sequence is convergent. So monotone or monotonic sequence. Every bounded and monotonic sequence is convergent, or all bounded monotonic sequences are convergent. This is the statement of the monotone convergence sequence. That means a monotone sequence or monotonic sequence is convergent when it is bounded. When it is bounded. So how can we prove? Let Sn be bounded and monotone sequence. Let Sn be bounded and monotone sequence. Now we have to show this is convergent. So we know what is the definition of the monotonic sequence. Monotonic sequence or monotonic sequence means it is either increasing or decreasing. So sequence is either increasing or decreasing. First I will take first case one. So case one, let Sn is increasing. Let Sn is increasing. So let capital S equal to set Sn n belongs to n. That means S is a set S1, S2, S3, S4 and so on. So Sn n belongs to n. So in other words, capital S is the range of the sequence Sn. So capital S equal to set S1, S2, S3 and so on. So This implies S is bounded because a given sequence is bounded. Since a sequence is bounded, the automatic set S is bounded. So S is bounded means it is bounded below and bounded above. So when you say a set is called bounded, or when you say sequence is called bounded, it is bounded below and bounded above. So therefore it is bounded, this implies S is bounded above. So we know that the completeness exam, last class I told completeness exam means every non-empty subset of R which is bounded above has a supremum. And also similarly, every non-empty subset of R, subset of real numbers, R means the real numbers, which is bounded below, has a infimum. Here now it is bounded above. By completeness exam, S has a supremum. This set has it is a real sequence, so it is a subset of R, S is a subset of R, and it is a bounded above. It has a supremum. By completeness exam, S has supremum. So let U is equal to supremum of set S. That means supremum of the sequence. In other words, U is the supremum of the sequence Sn. In other words, or supremum of set S means supremum of the sequences. So by completeness exam, S is supremum. Let supremum of the set S or the supremum of the sequence Sn is let U is equal. Now we have to show our claim is, or we have to show Sn converges to U. That means we have to show Sn converges to the supremum of the sequence. Supremum S means supremum of the sequence. So now we have to show Sn converges to U. That means we know when you say Sn converges to S, for any epsilon greater than 0, there exists a number, natural number n greater than 0, n such that mod Sn minus S less than epsilon for all n greater than n. So now let epsilon greater than 0. This implies U minus epsilon is not upper bound of S. Why? It is U. This implies let epsilon greater than 0. U minus epsilon is not upper bound of S since U minus epsilon less than U. So what is the so here U is supremum. Supremum is least upper bound. What is the meaning of the least upper bound? What I told already. Least upper bound means it is an upper bound, and any number less than M is not upper bound. Any number less than M is not upper bound of the sequence. So now U minus epsilon is less than epsilon because U is the least upper bound. Therefore, U minus epsilon is not upper bound of S because U is the least upper bound of the sequence or least upper bound of the set S. So U minus epsilon is not upper bound of S since U minus epsilon less than U and U is the supremum of S, that is least upper bound of S. That's why it is not upper. So it is not upper bound means what is the when you say an upper bound? U minus epsilon is called upper bound if Sn less than or equal to U minus epsilon for all n belongs to n. Where it is not upper bound means there exists a number capital N such that n belongs to n, natural number, such that U minus epsilon less than Sn because it is not upper bound. If it is upper bound, then Sn always less than or equal to U minus epsilon for each n. Since it is not upper bound means some number, there exists some number n such that U minus epsilon less than Sn because it is not upper bound. If it is upper bound, what happens? Sn is less than or equal to U minus epsilon. Every number in the set is always less than or equal to U minus epsilon when it is upper bound. It is not upper bound means there exists a number n such that U minus epsilon less than Sn. In other words, there exists an element in the set S such that U minus epsilon less than Sn. All the elements are the terms of the sequence Sn. So that's why I have written there is this number capital such that U minus epsilon less than Sn. U minus epsilon less than Sn. So, since Sn is increasing, so when Sn is increasing implies S capital N less than or equal to Sn for all n greater than n. So increasing means so for all, for example, capital N is 2 is small n equal to 4. That means S2 less than or equal to S4. So since Sn is increasing, S capital N less than or equal to Sn for all n greater than n. So Sn less than or equal to Sn since Sn is increasing. Already I have given another definition. So a sequence Sn is called increasing if Sn greater than Sm for all n greater than n. So here it is n greater than n. That means Sn less than or equal to Sn. Here capital N less than n. That's why S capital N less than or equal to Sn. So since Sn is increasing, so by 1 and 2. So here by 1 it is not upper bound. You get U minus epsilon less than Sn. This is less than equal to Sn. And U is an upper bound. Why? Because U is supremum. Supremum means it is an upper bound already. When we say supremum, it is an upper bound, and any number less than m is not upper bound. So U is an upper bound. U is an upper bound. So upper bound means every term in the set is less than equal to U. So upper bound means every term, every element in the set S is always less than equal to U. So since supremum of S equal to U, U means this is an upper bound. So every term in the set S is less than equal to U. And also epsilon positive U less than U plus epsilon. Because why? Because this is U is less than U plus epsilon. Since epsilon is positive, finally you get U minus epsilon less than Sn less than U plus epsilon for all n greater than n. That means mod Sn minus U less than epsilon for all n greater than n. Already I told C minus delta C minus epsilon less than here. This can be written as minus epsilon less than Sn minus epsilon less than U plus epsilon. So this is less than minus epsilon less than Sn minus U less than. So this means U minus epsilon less than Sn less than U means mod Sn minus U less than epsilon for all greater. Therefore, limit Sn equal to S. Therefore, sequence Sn converges to U. That is supreme of the sequence. So simple. This is first we let capital S equal to Sn and belongs to N. Simple as S is bounded because sequence Sn is bounded. Bounded means it is bounded above below. So bounded above by computing this exam, S has supremum and let U is equal to supremum of S. So now we have to show Sn converges to U. So to show this, let epsilon greater than 0. Therefore, U minus epsilon is not upper bound of S. Why? Because since U minus epsilon less than U and U is a supremum. Supremum means it is the least upper bound. Least upper bound means any number less than U is not upper bound. So U minus epsilon is not upper bound. Whenever it is not upper bound means there is some number n such that U minus epsilon less than Sn. Because if it is upper bound, every term is less than equal to U minus epsilon. It is not upper bound, some element, there exists a number n capital such that U minus epsilon less than Sn. And since it is increasing Sn less than plus N for all n greater than n. S capital N less than plus N for all n greater than by definition of increasing. So from 1 and 2 we write U minus epsilon less than Sn. This is less than equal to Sn. This is less than equal to U because U is an upper bound. U is the supremum of S is upper bound. That is less than U plus epsilon because the epsilon positive U less than U plus epsilon. So finally get U minus epsilon less than Sn less than U plus epsilon. Therefore, from this mod Sn minus U less than epsilon for all n greater than. Therefore, limit Sn equal to U. Therefore, sequence Sn converges to U. So sequence Sn converges to supremum of the sequence. So similarly, if Sn is a decreasing, so then minus Sn is increasing. It is bounded, it is also bounded. So by case 1, minus Sn is convergent and limit minus S equals supremum of minus S. So if Sn is decreasing, minus Sn is increasing. For example, if you take Sn equal to 1 by n square, Sn equal to n square. N square means we get the sequence Sn is 1, 4, 2 square means 4, 3 square means 4, 1, 4, 9. So it is increasing. Yes, sir. It is, for example, Sn equal to 1 by n. If you take Sn equal to 1 by n square, you get 1, 1 by 4, 1 by 9, it is decreasing. So minus Sn means minus 1 by n square, that is minus 1, minus 1 by 4, minus 1 by 9. This is the increasing. So Sn is decreasing, then automatically minus Sn is increasing. And by case 1, minus Sn convergent, and the limit of minus equals supremum of minus. But the supremum of minus is equal to minus infimum of S. So minus minus will be cancelled. We get limit Sn equal to infimum of S. So sequence converges to infimum of sequence when it is a decrease. Finally, if it is increasing and bounded, then it converges to supremum of the sequence. And if it is a decreasing and bounded, then it converges to infimum of the sequence. And also we observe that if it is increasing, every increasing sequence is bounded below. It is enough to show an increasing sequence is convergent is enough to show bounded above. Because whenever it is increasing, it automatically it is bounded below. So to show an increasing sequence is convergent, it is enough to show it is bounded above. Because whenever it is increasing, automatically it is bounded below. And also every decreasing sequence is bounded above. Bounded above by S1. Every term in the sequence is less than or equal to S1. So it is bounded above when it is decreasing. Sn is decreasing, then it is bounded above. To show it is a convergent, it is enough to show bounded below. So bounded below. Finally, we are getting an increasing sequence which is bounded converges to supremum, and decreasing sequence converges to its infimum. So these are the main points, because a sequence which is increasing and bounded above converges to the supremum of sequence. So whenever it is increasing, automatically it is bounded below. So in the monotonic convergence theorem, that means it is a monotonic sequence. It is enough to show bounded. Whenever it is increasing, automatically it is bounded below. It is enough to show bounded above. So increasing and bounded above converges to supremum of the sequence. And whenever it is decreasing, automatically it is bounded above. Every decreasing sequence is bounded above. To show it is bounded is enough to show bounded below. So these two are enough. Whenever it is which is decreasing and bounded below converges to infimum of sequence. So to show, suppose the sequence is increasing, it is enough to show convergent, it is enough to show bounded above. If it is decreasing, it is enough to show bounded below, whether it is convergent or divergent. So we see one or two problems. Let S1 equal to 1. S1 equal to 1. Sn plus 1 equal to 1 by 3 Sn plus 1 for n greater than 1. So find S1, S2, S3. Use induction to show Sn greater than 1 by 2 for all n. Show limit Sn exists and find limit Sn. So already by definition S1 is 1. S2 means writing in place of n is equal to 1, you get S2. So 1 by 3 S1 plus 1. So what is S1 here? 1. So 1 plus 1 by 2. 1 plus 1 by 3, you get 2 by 3. So here writing n is equal to 1, you get S2, 1 plus 1 S2. So here S1 plus 1, that is 1 plus 1 by 3, that is 2 by 3. If you write n equal to S3, 1 by 3 S2 plus 1. So what is the S2 here? S2 here 2 by 3 plus 1. Here S2 is 2 by 3 plus 1. So that means 2 plus 3, 5 by 3. So 2 plus 3, 5 by 3, 5 by 3 into 1 by 3, that is 5 by 9. So S1 is 1, S2 is 2 by 3, S3 is 5 by 9. So we observe here S1 is greater than S2, S2 is greater than S3. So we observe this is a decreasing sequence. This is decreasing sequence. We observe. So by observing S1 is 1, S2 is 2 by 3, S3 is 5 by 9, S4 is 1 by 3, 5 by 9 plus 1. That means 14 by 27 will get. So it is a decreasing sequence just by observation. So we use induction to show Sn greater than 1 by 2. So here S1 is 1. So what is induction? Mathematical induction means first we show it is true for n is equal to 1, and let it is a true for n is equal to k, and then it is to prove it is true for n is equal to k plus 1, then automatically it is true for all n. So now we have to show second one Sn greater than 1 by 2 for all n using mathematical induction or by induction. So here S1 equal to 1. This is greater than 1. 1 is greater than 1 by 2. Therefore, it is true for n is equal to 1. So it is true for n is equal to 1. Let it is true for k. N is equal to k means, so let Sk is greater than 1 by 2. Let Sk. Now we have to show Sn greater than 1 by 2. To show this, you use a mathematical induction. So first I will take S1. What is S1? S1 equal to, by definition already given, S1 is 1. So S1 equal to 1. 1 is greater than 1 by 2. So therefore it is true for n is equal to 1. Let it is true for n is equal to k. Let Sk greater than 1 by 2. Sk greater than 1 by 2. So what is Sk greater than 1 by 2 implies? So Sk plus 1 greater than 1 by 2 plus 1. So if you take Sk plus 1 greater than 1 by 2 plus 1 and 1 by 3 Sk plus 1 greater than 1 by 3 1 by 2 plus 1. So if you adding 1 Sk plus 1 1 by 2 plus 1, Sk plus 1 greater than 1 by 2 plus 1, and it is greater than 1 by 3 into Sk plus 1 greater than 1 by 3 1 by 2 plus 1. So we'll get 1 by 3 Sk plus 1 is Sk plus 1. What is the definition? Sn plus 1 is 1 by 3 Sn plus 1. So I will write here 1 by 3 Sk plus 1 is a Sk plus 1. And 1 by 2 plus 1 is 1 plus 2. 3 by 2. 3 will be cancelled, get 1 by 2. So here 1 by 2 plus 1 is 3 by 2. 3 cancel, you get 1 by 2. So finally you get sk plus 1 greater than 1. So it is true for n is equal to k plus 1. Therefore by induction Sn greater than 1 by 2 for all n. So first I have shown for n is equal to 1 it is true, S1 equal to 1 greater than 1 by 2. Let it is true for k, sk greater than 1 by 2. And it is true for sk plus 1 is greater than 1 by 2. So sk greater than 1 by 2, let if you take 1 by 3, sk plus 1 greater than 1 by 3, 1 by 2 plus 1, this is 3, we can say sk plus 1 greater than 1. So therefore by induction Sn greater than 1 by 2. That means every term the sequence greater than 1 by 2. This is like Sn greater than some k1, k1 less than S1, that is Sn is bounded below. Sn is a bounded below by 1 by 2. Bounded below by 1 by 2. So every term in this sequence is greater than 1 by 2. That is, it is bounded below. It is bounded below. And also we call this 1 by 2 is lower. This is like k1 less than Sn. K1 less than Sn. So it is bounded below. So whenever it is increasing, automatically it is bounded above. So there is no need of to show bounded above, because to show it is enough if it is decreasing. How can we show decreasing? What is the decreasing definition? A sequence is called decreasing Sn plus 1 less than Sn for all n, or Sn plus 1 minus Sn less than greater than equal to 0. So first we see I have to show Sn plus 1 less than Sn for all n to show decreasing. So this can be also I have to prove using induction. To show by using induction, first I will prove this it is true for n is equal to 1. N is equal to 1 means S2 is less than S1. Why? Because it is true. What is S2? S2 is 2 by 3. S1 is 1. So 2 by 3 less than 1. So we can observe here it is a decreasing sequence. First term is 1. Second term 2 by 3 decreasing. Third term is 5 by 9. So S2 less than S1. So that means S1 greater than S2. S2 less than S1. Since S2 is 2 by 3, S1 is 1. 2 by 3 less than 1. So therefore it is true for n is equal to 1. N is equal to 1, it is true. Let it is true for n is equal to k. So that means n is equal to k. Sk plus 1 less than sk. So this implies adding 1. We'll get sk plus 1 less than sk plus 1. And 1 by 3 sk plus 1 plus 1 less than 1 by 3 sk plus 1. This can be written as sk plus 2. This can be written as sk plus 1. Why? Because Sn plus 1 equal to 1 by 3 Sn plus 1. Sn plus 1 equal to 1 by 3 Sn plus 1. So 1 by 3 sk plus 1 can be written as sk plus 1. This can be written as in place of n, k plus 1 is there, n plus 1, that is k plus 2. So we know that 1 by 3 Sn plus 1 is Sn plus 1. Here in place of n, k plus 1 is there, we get k plus 2. Sk plus 2 less than sk plus 2. So it is true for n is equal to k plus 1. So by induction, it is true for all. So how can I show? How can we show this? First, I have shown it is true for n is equal to 1. N is equal to 1 means 1 plus 1, 2. S2 less than S1. Since 2 by 3 less than 1, because S2 is 2 by 3, S1 is 1. So Sk plus 1 is less than Sk. So adding 1 and 1 by 3 Sk plus 1 plus 1 is 1 by 3 Sk plus 1. So Sk plus 2 less than Sk. Therefore, by induction, Sn plus 1 Sn less than 4. It is true for n equal to k plus 1. Therefore, by mathematical induction, Sn plus 1 less than Sn. Therefore, a sequence Sn is decreasing. Whenever it is decreasing, automatically it is bounded above. Every decreasing sequence is bounded above. Therefore, it is bounded, already bounded below, bounded above. So we get by monotonic convergence, Sn is convergent and limit Sn exists. Limit Sn exists. So, or you can simply observe here, S1 is 1, S2 is 2 by 3, S3 is 5 by 9, S4 is 1 by 3, 5 by 9 plus 1. That is 14 by 27. So it is decreasing. Sequence is decreasing. 1, 2 by 3, 5 by 9, 14 by 27. So it is a decreasing sequence. Whenever it is decreasing, it is automatically bounded. Already we have shown bounded, that is, it is bounded. So by monotonic convergence theorem, Sn is convergent and the limit Sn exists. Limit Sn exists. So now we have to find out the limit Sn. So let limit Sn equal S. Automatically limit Sn plus 1 is also S. How? Because it is a subsequence of Sn. Sn plus 1 is subsequence of Sn. So limit Sn plus 1 also is equal to S. So from 1 already, what is Sn plus 1 actually? Sn plus 1 is 1 by 3 Sn plus 1. Taking limit both sides. Limit Sn plus 1 is equal to 1 by 3 limit Sn plus 1. Taking both sides limit Sn plus 1 equal 1 by 3 limit Sn plus 1. So limit Sn plus 1 equal to S. This is 1 by 3 S. Because Sn plus 1 is subsequence of Sn. So these two are same. Sn, every subsequence converges to same point. So S equal to 1 by 3 S plus 1. We get 3S equal to S plus 1. 3S minus S is 2S that equal to 1. S equal to 1 by 2. Limit Sn equal to 1. Because here 1 by 2 is the GLB. That's why it converges to 1 by 2. This is so it is decreasing, it is enough to show bounded below. It is increasing, it is enough to show bounded above. See another interesting example. So that the sequence defined by S1 equal to 5, Sn equal to Sn minus 1 square plus 5 by 2 Sn for n greater than equal to 2 is convergent. Here C is missing. For convergent is convergent and find its limit. So find its limit. First we see here given S1 equal to 5, Sn equal to Sn minus 1 square plus 5 by 2 Sn minus 1 for n greater than equal to 2. So this implies S1 is 5. Now I will show Sn greater than root 5. So the Sn greater than root 5, and then it is decreasing. So it is a decreasing sequence and bounded to show it is convergent means whenever it is decreasing, it is enough to show below, because automatically whenever it is decreasing, it is bounded up. So bounded below means it is greater than some number. So I will take root 5. So S1 equal to 5 greater than root 5. So now I will show, my aim is to show Sn greater than root 5. This can be shown by induction, by mathematical induction. I will show this by mathematical induction. So S1, given S1 is 5, this is greater than root 5. So it is true for n is equal to 1. So let Sk greater than root 5. That is, it is true for n is equal to k. First I have shown it is true for n is equal to 1. Let it is true for n is equal to k. Sk greater than root 5. I have to show it is true for n is equal to k plus 1. So see Sk plus 1, I have to show Sk plus 1 greater than root 5. So I will take Sk plus 1 minus root 5. What is the by definition? If you write it here n equal to k plus 1, you get k plus 1 minus k, Sk square plus 5 by 2 Sk minus root 5. If I write here n equal to k plus 1, Sk square plus 5 by 2 Sk minus root 5. So minus root 5. So LCM is 2 Sk. Sk square plus 5 minus 2 root 5 Sk. Minus 2 root 5 Sk. This is like A square plus B square minus 2AB. A is Sk, B is root 5. A square is Sk square plus B square is root 5 square is plus 5. Minus 2AB is minus 2 Sk root 5 minus 2 root 5 Sk by 2 Sk. So we observe the Sk is greater than root 5. So Sk is greater than root 5, it is positive number. Sk minus root 5 is positive number. So this is greater than 0. So Sk is a number greater than root 5. Here Sk minus root 5 is positive. This is positive. We'll get positive. So Sk is greater than root 5 plus Sk minus root 5 greater than 0. So numerator will get positive. Denominator is also positive because Sk is root 5 is positive. So we'll get greater than 0. Finally, get Sk plus 1 minus root 5 greater than 0. That means Sk plus 1 greater than root 5. So here we are getting Sk plus 1 minus root 5 greater than 0. That is Sk plus 1 greater than root 5. So it is true for n equal to k plus 1. This is by induction Sn greater than root 5 for each. So by induction Sn greater than root 5 for each n. By induction Sn greater than root 5 for each n. So therefore bounded below. Sn is bounded below. And also we observe the decreasing sequence. If you take here S1 equal to 5, so S2 is S1 square, 5 square, 25, plus 5, 30, 30 by 10, 3. So S1 is 5, S2 is we will get 30 by 10, 3. S3 is S2 square, 9 plus 5, 14, 14 by 6. 14 by 6 means 7 by 3. It is a decreasing sequence. So to show Sn is decreasing, we have to show Sn plus 1 minus Sn less than epsilon or less than P. So Sn plus 1 minus Sn. What is Sn plus 1? You write n is equal to n plus 1, we will get Sn square plus 5. So writing n is equal to n plus 1, we will get Sn square plus 5 by 2 Sn. That is minus Sn. LCM is 2 Sn square. We will get Sn square minus 2 Sn square. It is plus 5. Sn square minus 2 Sn square minus Sn square. It is 1 minus 2. Sn square minus 2 Sn square, we get 5 minus Sn square by 2 Sn. Here denominator is positive because Sn greater than root 5, Sn is positive. So 5 minus Sn square. So Sn square greater than 5. That is a 5 minus Sn square minus 5 is greater than 0. That is 5 minus Sn square is less than 0. Because here Sn is greater than root 5. Sn square greater than 5. That's why 5 minus Sn square less than 0. So it is less than 0. Here we are getting root 5 minus root 5 less than Sn. That is 5 less than Sn square. That is 5 minus Sn square less than 0. So numerator is negative. Denominator is positive. This is less than 0. We'll get Sn plus 1 minus Sn less than 0. That means Sn plus 1 minus Sn less than 0 means Sn plus 1 less than Sn for all n. So therefore Sn is decreasing. So Sn is decreasing means it is bounded above. Already we have shown bounded. So it is bounded. Therefore it is convergent. So whenever it is decreasing, it is enough to show bounded below. Whenever it is increasing, it is enough to show bounded above. So it is simple in decreasing. Already first I have shown Sn greater than root 5. And then to show Sn is decreasing, Sn is decreasing. Sn plus 1 minus Sn square plus 5 by 2 Sn minus Sn. That is a 5 minus Sn square. So Sn square plus 5 minus 2 Sn square. That is a Sn square minus 2 Sn square minus Sn square. 5 minus Sn square. Here Sn greater than root 5. That is root 5 less than Sn. That is 5 less than Sn square. So 5 minus Sn square less than 0. Numerator is negative. Denominator is positive. Okay. So this implies Sn plus 1 less than Sn. You don't worry. Here, suppose if I take Sn equal to 3, 3 greater than root 5. So root 5 minus 2 point something. So if I write 3 here, what happens? 5 minus N, negative. So Sn is decreasing. Decreasing already bounded here, therefore it is convergent. The monotone convergent, it is convergent. Here C means it is convergent. So by monotone convergence, given sequence is convergent. So let a limit Sn equal to S, automatically limit Sn minus 1 equal to S, because Sn minus 1 is subsequence of S. Sn minus 1 is subsequence of S. So therefore S limit of Sn minus 1 square plus 5 by 2 Sn. S equal to S square plus 5 by 2S. Because it is subsequence of this. So that's why S is equal to S square plus 5 by 2S. You get 2S square equal to S square plus 5. S square equal to 5. Here we get two values. One is S equal to plus or minus root 5 will get. Here we get two values. S equal to plus or minus root 5. So S must be equal to plus root 5 because S cannot be not equal to minus root 5 because since Sn greater than root 5, this implies limit Sn greater than root 5. So that's why limit Sn equal to root 5. Here we get the S has two values, S equal to plus or minus root 5. But it is not equal to minus root 5 because every element is greater than root 5. That's why limit Sn equal to root 5. Since limit Sn greater than root 5. Let's see another problem. So whenever it is decreasing, it is enough to show it is bounded above. It is enough to show it is bounded below. Whenever it is increasing, it is enough to show it is bounded above. So that the sequence Sn equal to 1 plus 1 by n whole power n is convergent. So this is 1 plus x whole power n. So 1 plus x whole power n is 1 plus nx plus n into n minus 1 by 2 factorial x square plus and so on, n into n minus 1, n minus 2 and so on into 1 by n factorial x power. So 1 plus x whole power n equal 1 plus nx, n into n minus 1 by 2 factorial x square, n into n minus 1, n minus 2 and so on by n factorial. So here 1 plus x whole power is 1 plus nx, x is 1 by n, n is 1 by n, and we have to write nc2. This is n into n minus 1 by n 2 factorial into x square 1 by n square and so on. N into n minus 1, n minus 2 and so on into 1 by n factorial and so on 1 by n power n. So this is the formula I have used. 1 plus nx n into n minus 1 by 2 factorial x square n into n minus 1 n minus 2 and so on 1 by n factorial x power n. So here 1 plus nx x is 1 by n. So n will be cancelled, get 1 plus 1 by n. And the third term, here 1 n will be cancelled. And here 1 by 2 factorial. N minus 1 by n. N will be cancelled, 1 minus 1 by n. So here n will be cancelled. So n minus 1 by n is 1 minus 1 by n. So on 1 by n factorial. Here n power n means n into n times. 1 n when we cancel 1, here we get 1 by n factorial. N minus, here we get n power n. Here I have written here n square, n by n 1, n minus 1 by n. Similarly, here n by n, n minus 1 by n is 1 minus 1 by n. N minus 2 by n is 1 minus 2 by n. Here I am writing, I have to get 1 by n. This can be written as 1 minus n minus 1 by n. That is n minus n by n. That is we get 1 by n. I am writing this n power n, 1 n here. Here I have written, how can I have written here n square, n by n, 1. This is n minus 1 by n is 1 minus 1 by n. So here n square is there, 1 n here I have written, n by n is 1, n minus 1 by n is 1 minus 1 by n. And here n power n means n into n times, 1 n here, n by n 1. 1 n here, n minus 1 by n is 1 minus 1 by n. 1 n is here, n minus 2 by n is 1 minus 2 by n. And so on. Here 1 can be written, I have to get here 1 by n. 1 by n means 1 minus n minus 1 by n. This is n minus n cancel 1 by n. So we'll get 1 by n. Similarly, Sn plus 1 is 1 plus 1 by n plus 1 whole power n plus 1. Similarly, Sn plus 1 is 1 by n plus 1 whole power n plus 1. That is 1 plus 1. Similarly, just to write here 1 by 1 minus 1 by n plus 1, 1 by n plus 1 factorial, 1 minus 1 by n plus 1, 1 minus 2 by n plus 1, and so 1 by minus n by n plus 1. Actually, here first two terms are same in Sn and Sn plus 1. And since 1 minus 1 by n always 1 minus 1 by n plus 1. For example, why? Because this. We know that 1 by n is greater than 1 by n plus 1. Minus 1 by n less than 1 by n plus 1. So minus 1 by n less than minus 1 by n plus 1. So that's why 1 minus 1 by n less than 1 by n by n. For example, if you take n is equal to 1, what happens? 0 here it is. It is 1 by n is equal to 2. This is 1 by 2. It is 2 by 2. So 1 minus 1 by n less than 1 minus 1 by n plus 1. So this is less than this. Similarly, 1 minus 2 by n less than 1 minus 2 by n plus 1. And 1 minus 3 by n less than 1 minus 3 by n plus 1. And so on. 1 minus n minus 1 by less than 1 by 1 minus n by n plus 1. Using these equations. So here, every term in Sn less than every term in this. First two terms are same. So this is less than this is. Similarly, every term is less than this. And this is extra term. So finally getting Sn less than Sn plus 1 for each. That is, given sequence is increasing. Given sequence is increasing. So Sn less than Sn plus 1 means Sn plus 1 greater than Sn. Sn plus 1 is greater than Sn. That is, Sn is increasing. Sn less than Sn plus 1 means Sn plus 1 greater than Sn. That is, Sn is increasing. Here simple, this is the first two terms are same here. 1 plus 1, here 1 plus 1 same. Here 1 minus 1 by n less than 1 minus 1 by n plus 1. Or 1 minus 2 by n less than 1 minus 2 by n plus 1. That's why Sn less than Sn plus 1. So given sequence is increasing, therefore it is increasing, automatically it is bounded below. It is enough to show bounded above. It is enough to show bounded above. And so by 1 here Sn less than 1 by, because 1 minus 1 by n less than 1. So that's why it is less than 1 by 2 factorial. And 1 minus 1 by n 1 is less than 1. 1 minus 2 by n less than 1. 1 minus n minus 1 by is less than 1. That's why this can be written as Sn less than 1 plus 1, 1 by 2 factorial, 1 by 3 factorial plus 1 by 1 factorial. And also 1 by 2 factorial is 1 by 2. 1 by 3 factorial means we get 1 by 2 into 3. We get 1 by 2 into 3. This can be less than 1 by 2 into 2. So 1 by 2, 3 factorial means 1 by 1 into 2 into 3. 1 by 2 into 3. This is less than 1 by 2 into 2. That is 1 by 3 factorial less than 1 by 2 square. So 1 plus 1, 1 by 2 less than 1 by 3 factorial is 1 by 6 less than 1 by 4. So similarly 1 by n factorial is less than 1 by 2. How can we get this? See, 1 by n factorial is, since 1 by n factorial is 1 by 1 into 2 into 3 into n. Here 1 into 2 I will write 1 by 3 less than 1 by 2. And 1 by 4. Next we'll get 1 into 3 into 4. 1 by 4 less than 1 by 2. 1 by 5 less than 1 by 2. 1 by n less than 1. So we'll get 1 into 2 into 2. Here from 2 onwards it is n minus 1 terms. That's why 1 by 2 power n minus 1 by n factorial less than 1 by 2 power n minus 1. So for n greater than or equal to 2. It is for n greater than or equal to 2. So here 1 minus 1 by n less than 1. That's why I'm writing 1 by 2 factorial. This is less than 1. This is less than 1. This is less than 1. So every 1 minus 1 by 1 less than 1. 1 minus 2 by n less than 1. 1 minus n minus 1 by n less than 1. So you get 1 plus 1, 1 by 2. 1 by 3 factorial less than 1 by 2 square. 1 by n factorial less than 1 by 2 power n. So here we're getting 1 less than 1 by 2 into 2 into and so on. That is 2 power n minus 1. Finally get Sn less than. And this is like, it is a geometric progression. It is in GP. 1 plus r square r power n minus 1. This is 1 minus r power n by 1 minus r. Here r is a 1 by 2. Here r is a 1 by 2. So we can write Sn less than 1 minus 1 by 2 power n by 1 minus 1 by 2. So here we're getting 1 minus 1 by 2 is 1 by 2. 1 by 2 by 1 is 2. So here 1 minus 1 by 2. Here 1 minus r power n by 1 minus r. R is 1 by 2. Here r is 1 by 2. So we finally get 1 minus 1 by 2 is 1 by 2. 1 by 2 means you get 2 into. So here 1 by 2, 1 minus 1, 2 into. By reversing 2 into 1 minus 2 power. Finally 1 plus 2, 3. 3 minus 1 by 2 power n minus 1. Here means 2 into 1 by here. We have to get 2 power n minus 1. This is less than 3. So this is less than 3. So here 1 by 2 power n minus 1 here to get here. So Sn less than 3 because 3 minus something. This is Sn less than 3. Therefore, it is bounded above by 3. Already it is increasing means it is bounded. Therefore, by MONOTONE convergence theorem, it is converged. And also it converges to E because it lies between 2 and 3. Sequence converges to E. It's a well-known limit. Limit intersection plus 1 is E, where E lies between 2 and 3. It is something 2.7 something. Okay. This is the today's class. Thank you.